start with saying a few words about what we did last time, what we will do today, and a few other notes. So let's maybe start with other notes. First, the exercises. Do them, they are important. I was quite surprised last time to hear that someone was under the impression that you were only asked to do the exercises for the time when you're going to present. Well, we are not checking if you're doing the exercises. You're supposed to be able to take that responsibility yourself, but they are important for the course and they cover also quite important material. So I strongly suggest you to do the exercises. Then, when I went through the notes last time, I noticed a few typos in the lecture notes. So these notes of this part of the course, they are not as old as Patty, so they haven't been around, and I'm redeveloping them heavily, so new typos are also introduced. So I found a few SO2s that should be SO3s in the lecture of last time. I believe it should be fairly obvious, but now you're warned. Please report typos. It's very helpful when you do so. Okay, so now we come to the actual subject of matter. So last time we spent a lot of time talking about the group SO3. And we went through the 2l+1 dimensional representation and the algebra, and towards the end we came to the sort of sister group SU2. Today we will continue where we ended with SU2, and we will in particular talk about start out with the algebra. Well, that we will finish up soon. We will consider the homomorphism between the groups SU2 and SO3. Between these sister groups, they are homomorphic, they are not isomorphic. And we will explore the 2j+1 dimensional irreducible representation. So I just call the letter L here that we have from SO2, SO3 here, J here. It's not only renaming. We will find that these J's are slightly different than those L's in the sense that there are more of them. Then we will also spend a lot of time and definitely a lot of pages discussing the direct product space. And we will encounter the Clebsch-Gordon decomposition of this direct product space and the Clebsch-Gordon coefficients that you should recognize from other courses. So any questions or comments before we actually start? Okay, so then let's start where we ended last time. So just scroll up to see what we had here. So we have the SU2 algebra. So this is what I'm continuing with here. And we had just about figured out that the SU2 algebra can be written in the physicist choice, that is with Hermitian matrices, essentially like this, that is using the sigma matrices. So essentially the generators are the sigma matrices. And the group elements can be generated like this. And then we found this commutation relation for the generators that we also recognized from SO3. So it's exactly the same commutation relations as for SO3, although the group is SU2. Okay, so now let's come to new stuff. So now we will consider the space H2. So this is the space of Hermitian 2x2 matrices, treated as a real three-dimensional vector space. So what we will do is that we will consider an isomorphism from R3 to H2. And what this isomorphism will do is that it will take the basis vector Fi in R3 and map it onto sigma 1, sigma I. So X hat will be mapped to sigma 1, Y hat will be mapped to sigma 2, etc. And the general vector will then be mapped into a linear combination of the sigma matrices by this map. So this is, of course, then a 2x2 matrix. and we have this map between ordinary vectors in our ordinary space to 2 times 2 emission matrices. Now, it actually turns out, and we will soon see it, that we can define a scalar product on this space. The scalar product between two vectors x moved to this H2 space will be constant times the trace of the two matrix representations of these vectors. So let's see a little bit why that makes sense. So to see why this makes sense, we note that the trace of sigma I, sigma j, well, if sigma I and sigma j are the same, so if I and j are equal, then what we have here is nothing but two-dimensional unit matrix, because sigma I squared is 1. So this is then 2. If I and j are not equal, recall that this product of sigma I and sigma j is just some sigma k, so it's some I epsilon ijk sigma k. So we have just another sigma matrix. So we have some trace of some sigma k. But sigma k is traceless, so this is 0. So in other words, the scalar product would be non-vanishing only if it has the same spatial coordinates. So if both vectors have an x coordinate, both vectors have a y coordinate, so both vectors have a z coordinate. Okay, and this we will use for this famous homomorphisms at the group level. So it's a little bit confusing perhaps because we have an isomorphism at this level. So this map is 1-to-1. But when we consider the group action, what the group does to this, we will have a homomorphism and it will no longer be 1-to-1. Okay, so now we come to this rather important result, namely that we can rotate a vector x in H2 by using a 2 times 2 Hermitian matrix U in SU2 in the following way. So note here that this is how you would normally rotate the matrix. And now X is indeed this 2 times 2 matrix, and you are rotating it by U dagger, that is U inverse and U. So this is how you would normally rotate the matrix. We will see that this makes sense by considering the scalar product. So normally if we rotate vectors in 3-dimensional space, their scalar product is invariant, and we will want then the same property here. So let's see what we get. So we have then x dot z for some vectors in H2. The scalar product is defined as 1/2 trace x times z. By the way, this factor of 1/2 standing here, it is of course to compensate for this factor of 2 up here, that trace sigma I squared is 2. Okay, so it's this thing. The components, the scalar component x, y, and z I of x and z, we can break out, and what remains in the trace is then the sigma matrices. And as we have seen, this trace is only non-vanishing if the indices here are the same. So it's 1/2 times 2 delta I j x I z j. So it's x I z I. That is, it's the scalar product between x and z as we recognize it from normal vectors, from ordinary R3 space. And we see now that the scalar product behaves exactly as we expect it to behave from R3. So this means that we can also introduce the concept of an angle in H2. So we can take the length of these and compare it to the scalar product and get the angle between them in this way. It is also important to check that we are staying in the H2 space by this action, and this is completely straightforward to check. So if we have u x u, then this is still an element in H2 because we still have something that is emission. Let's check. So we have u x u dagger, dagger. Daggering this whole object, we move this guy to the other side, and it becomes an additional dagger, that dagger. So dagger, dagger, that is no dagger, and we get this. And then we have x, and then we have u dagger from this guy. So obviously this is still emission if this guy was emission. But what we have is also something that is still traceless because of the cyclicity of the trace. We can move this u, for example, to this side, and then we have u dagger u, and this is then 1. So if we started out with something that was traceless here, this thing is still traceless. Also, this map conserves lengths. So let's have a look. So we rotate then the vectors. We rotate the x vector, we rotate the z vector as we rotate matrices. Then we want to take the scalar product that was essentially defined as the trace. So it is the trace of the z vector from here and the x vector from here in rotated form. And again, we simply cancel some factors of u here. And we are back where we started. So this mapping conserves lengths. So both lengths and angles are conserved. So we have the same properties as for ordinary rotations in R3. Any questions so far? Okay, then let's continue. So we will now look into in a bit more detail how this corresponds to the rotations in R3. So we've seen that important properties are conserved, but now we will actually consider the form of the rotations and see what they look like. So we consider transformation in SU2. And this transformation can be written of the form e to I generators, and we have seen that we can expand it in this way or in explicit matrix form. We will consider a rotation around the z-axis for simplicity. So in this linear combination n hat sigma, we will only pick the z component. So n hat 3 will be 1 and the others will be 0. So it will be the sigma 3 axis. Okay, so now let's rotate the vector x then as we rotate the matrix. So it's some u, some x, and some u dagger. Now we actually don't have to use this form because we are rotating around the z-axis, so we have a diagonal matrix. So of course sigma 3 is diagonal 1 minus 1. So this is what we exponentiate up here. So it's e to minus I alpha over 2 because we had this over 2 up here. One diagonal and the other diagonal element is e to I alpha over 2. So this was this u here. Then the u dagger, or the inverse of this, well, we just change the angle. It's pretty trivial in this case. We change the angle to minus the angle. And in the middle we have the vector standing as a 2 times 2 matrix. Okay, here we just expand it out. So we have x. We have x from here. We have sigma 1 acted upon by this matrix and by this matrix. So let's see what happens here. So our sigma 1 is 0, 1, 1, 0. So this element here, that one element should pick up, will be multiplied by this component here. So we'll pick up a phase minus I alpha over 2. And then it will be multiplied with this component here. So it will be another minus I alpha over 2. So in total, we get this. It's a minus I alpha, no, over 2. Similarly, we follow what happens with the other entries. For sigma 2, we pick up similar phases, as it has non-zero entries in the same positions. Sigma 3 is trivial because it's diagonal, so it will once multiply this guy and once multiply this guy, so we'll have just a 1. And down here we will have this phase cancelling this phase, so we will have just the minus 1 from the sigma 3 itself. So then we want to decompose this vector, so we expand now and look at what we have multiplying the components sigma 1, sigma 2, and sigma 3. So for sigma 1, we have the cosine from here, and from here we have minus, minus, and then I squared, so that's minus sine y, and then the sine alpha from here. So and that's the real part here. So, and then similarly, we check what we have for sigma 2, and we check what we have for sigma 3. Sigma 3 is trivial, it is just this matrix standing here. Okay, so at the end of the page, we get this result for the rotated matrix. But now we want to translate this to see what happens to the components x, y, and z. So recall that the x component was whatever multiplied sigma 1, so it's this thing here. So to see what happens to x, we read off these components here. So we see that x have gone to this thing here, so it's standing here. Similarly, y has gone to this thing here, standing there, and z has gone to itself. So now I hope that someone recognizes this as something familiar, because if you look at it, I can see that at least Matthias is following this. So we see that we have actually an ordinary rotation. So this is what we get for an ordinary rotation in 3 dimensions around the z-axis. So the z-axis remains unchanged, and the x and y have changed as they do for an ordinary rotation. So in other words, we have done exactly the same as if we were rotating x in 3 dimensions around the e hat 3 axis. So this map up here has exactly the same effect as this map down here. So from this we conclude that the groups SU2 and SO3, which may not seem so similar at first sight, are actually quite closely related. So we have seen it before at the level of the algebra, because we have seen that we had essentially the same algebras, they were 1-to-1, and we had the same commutator, so we had the same commutator relation for the generators. But now we have found that we can actually find a map between the groups. So let's now have a look at the properties of this map. This will turn out actually not to be an isomorphism, but as I said, a homomorphism at the level of the groups. So at the level of the elements, we had this map up here, and this is clearly 1-to-1. The x and this x, they are 1-to-1. And now if we consider the action of rotation, we will find that we no longer have something that is 1-to-1. So we will now consider the group homomorphism that takes us from SU2 to SO3, where this homomorphism phi is defined as phi of u acting on x is what you get. If you first translate your x with f of x, so here you're in the Hermitian 2 times 2 space. Then you rotate in this Hermitian 2 times 2 space. So this is what's done here, as we rotate in this space. And then we transform back. So this is what's done by f inverse. So this f is 1 to the 1 and the f inverse is 1 to 1, but here something will happen. And this then on x defines rotation on x, as we have seen. So let's also try to visualize this graphically as done here. So we start with some x vector in some R3 space. Then we act with it on F. Then we move to some H2 space where the sigma matrices live, 2 times 2 Hermitian traceless matrices. Then we rotate it here, and this is done by U matrix U dagger. So we have some rotated matrix slash vector in this H2. Then we map back with F inverse, and then we are back to a real vector in R3. So that is what's happening here in this map. Okay. Then we will have a look at the properties now of this map. So that's homomorphism from SU2 to SO3. And for this homomorphism, we have the following property. So phi is surjective. So every possible image is mapped to by at least one argument. So we will find all possible rotations. We also have that the kernel of phi, so the elements that are mapped to the identity element in SO3. The identity element in SO3, that is no rotation. That kernel we will see is 1 and -1, and that is clearly isomorphic to group Z2, so cyclic two group. Okay, so let's have a look and see that we actually get no rotation if we do the if we insert the SU2 1 or SU2 -1 in this map from up here. So this is what is happening here. So we then have F inverse, the SU2 1 or the F, and then the F, and then the dagger slash inverse of this SU2 1. So if it's the 1, it's clearly the same, and then we're back to X. Then actually, if we instead consider the -1, what's happening here then is that we have a minus sign there, and we have a minus sign there that's intended to be a minus sign. So we have -1 squared, that is 1. So we are also back to X. So both these elements are mapped to the no rotation elements. So because of this, we find that some elements in the image are mapped to by more than one element in the name in the domain. And in fact, it's not only some, because if we instead consider a general U, here phi of and we consider phi of -u instead of phi of u. And if we insert this then in this map, we have F inverse, and then we have -u, and then we have the F of X, and then we have the -u dagger. Well, of course, these minus signs cancel again, and we see here that there is no difference between this expression and this expression. They are the same. So we will map to the same object as we do with U. So phi of minus u will be the same as phi of u will be r of x. And this is true for every u. So for every element r in SO3, we have that it's mapped to by two elements in SU2, let's say u and minus u. So we have a twofold cover of SO3. So in more group theory wordings, SU2 mod Z2 is isomorphic to SO3. So this is the reason for this double cover that you may have heard about at some point in quantum mechanics. We see here that we have two elements in one group mapped to one element in another group. This also means that we have seen very clearly that the groups SU2 and SO3, they are not isomorphic because we have this double cover. We have a homomorphism, but we don't have an isomorphism. However, their algebras, as we have seen, are the same. So we have now found what we sort of alluded to in the first lecture, that groups can be similar at the algebra level, but it doesn't imply that they are necessarily similar everywhere. So the algebra level is sort of the infinitesimal space around a group element, and there they are similar, but if one is considering the global properties, they are quite different. Any questions to that? Okay, then we move on. So now if we then compare the rotations in SO3 and SU2, we see that if we rotate by 2 pi in SO3, then we are back at identity. But if we rotate with 2 pi in SU2, we have -1. And this is because this factor of 1/2 that we have sitting everywhere in the representation. So it's because of this 1/2 sitting here. Note that to have this map, we could not have taken anything else but 1/2 here. We couldn't have taken a third here. So 1/2 is really special. 1/2 was essential to have this angle change ending up being 2 times 1/2 here. So to rotate with alpha. Okay, here the same thing is showed in picture in our ordinary space. If we rotate by just pi here, so so the point is that this vector here in our ordinary arc space is rotating around twice as fast as this vector here. But I think you got that point already, so I will not spend more time on it. Questions? Okay. Then we have a subgroup in this group, and the subgroup is U1. And the first thing that comes to my mind in this context, if I hear U1, is a diagonal matrix, a diagonal 1, 1, 1 matrix multiplying the same face. But that would not have a traceless generator, and it would not have the special matrix because it would not have determinant 1. But what we can do is to make this face up here cancel this face. So if we take this, all the u's given of this form, they will actually form a subgroup. Now this is entirely trivial to see, because if we just multiply two of these together, it will have the effects of adding up the arguments if we have one alpha 1 and one alpha 2 here. But we have different faces up here and up and down there. So in the subspace spanned by this vector, so acted on by the first guy here, we see that we have this e2 minus I over 2 times alpha. As we did for the SO2 group, we can then find other representations of this form here. We should obey the representation property that multiplying together two group elements, we should get a representation resulting in the representation of the resulting element. But that we clearly have. And 4 pi, as we have seen, then we need to rotate by 4 pi, by an angle of 4 pi to bring us back to the identity element. So e2 im 4 pi should be 1. And this means that m here, or some integer, not necessarily integer, some half integer m. The point is here that m can take on half integer values as well. So this is different from what we had for SO2 or SO3, where we needed to have full integer values. Here we can have half integer values, and this is the reason why we can have half integers spin. So as for SO3, we will then have 2j plus 1 dimensional representations. And j here will, however, be allowed to take half integers. So I'd like to now move into this section, but let's first see if someone wants to ask something. If not, I go on. So, as mentioned, there is then this one important difference that we can have half integer representations. So representations of SU2 can then be characterized by 0, 1 half, 1, 3 halves, 2, etc. Not only 0, 1, etc. So it's been 0, 1, etc. And the then 2j plus 1 dimensional irreducible representations of the Lie algebra of SU2 is characterized by an orthogonal basis, much as we did it for SO3. So we can copy paste all the map we did for SO3, and we can find find or construct orthogonal basis vectors. We construct them in such a way that d of j3, so j3, if I'm not bothering about writing out that it's a particular representation, dj of j3. On the state jm is then m times the same state as we had. So, and we can also define the raising and the lowering operators as we did before. So we have j plus and j minus is j1 plus minus I j2. And here is another result we can copy paste. So the math goes through exactly in the same way. So if we're acting with j plus minus on this state, we have this coefficient, the same coefficient as for SO3 acting on the state. Since we have the same algebra, we obviously have the same Casimir operator. So j squared is then represented by dj1 squared, dj j2 squared, dj j3 squared. And it has the same eigenvalues as before. So for the representation j, the eigenvalues is j times j plus 1. So same state here and same state here. So we have found more representations than we did in the SU2 case, but otherwise the structure is actually, so we have found more representations than in the SO3 case, but otherwise the structure is exactly the same in this SU2 case. And this means that we can also write down the elements of the representation dj of j plus minus. So what are these elements? Well, we see that we decrease or increase j by one number here. So whatever matrix we will get will be some matrix that is having zeros on the diagonals, and then if it is a j minus, it will have one step below the diagonal, and then it will be some normalization, and the normalization we will obtain from this. And the j plus looks the same, but we would then instead have elements sitting up here. So the representations of j plus and j minus can be obtained from this equation here. And by construction, by how we pick our basis vectors, we pick them in such a way that j3 is diagonal. So j3 is then m times delta m prime m. So this will be a diagonal matrix with the maximal value of m and all the way down to minus the maximal value of m. Okay, now we'll have a look at two representations that we encounter fairly, well, pretty much all the time, the two-dimensional representation and the one-dimensional representation. So first we consider then j is equal to 1/2. So this is the lowest dimensional representation that we couldn't have for SO3. And the states we then denote by 1/2, comma 1/2 and 1/2, comma minus 1/2. And we take this to be our basis vector, so 1, 0, 0, 1. And j3, so that should then be the matrix of eigenvalues to j3, and we should then have, we want it to be 1/2 for this guy, and we want it to be minus 1/2 for this guy. So note that I choose it in this way, such that acting on these states, which I then first pick, I get this diagonal form with values running from j to minus j. And of course, this is nothing but sigma 3 over 2. You should recognize this. Now we can act with the raising and the lowering operators on this state. So if we go up and look at the form of j plus, we have some coefficients in front. Here they are. And if we act with j plus on the state with 1/2 there, you will see by this big square root that you will have a 0 here. And similarly, just writing in the values, you will have a factor 1 there and the factor 1 there, and acting on j minus on the most negative m value here, we get 0. So we have this. And this means that we can identify the matrix representation. So the d1/2 representation of the dj plus element is then this thing. Why? Because it maps the this state, the lowest state, to this state. So we have this 1 here, and it maps everything, it maps the other vector to 0, and no vector here gets any component proportional to itself. So we have zeros on the diagonal. So as I said, it should be a matrix that is one step above the diagonal and be proportional to the unit matrix. And the proportionality constant here is just 1. And similarly, we find J minus. So we find that we have this form and this form. And then we see that this is actually 1/2 sigma 1 plus I sigma 2. I think that some of you would have thought that we could start the other way around, and knowing what we can, we could probably have done that. Starting with knowing that these were essentially the Jx and the Jy, and then we could have formed the linear combination corresponding to J plus, and similarly we could have formed the linear combination corresponding to J minus. And we could have done that, but we didn't. We actually recovered these forms here. And forming linear combinations of these, we actually recovered the representation of J1. So we didn't actually define it to be this thing, but we found that it was this thing, sigma 1 over 2. Because we found the form of J plus and J minus, because we defined because we had derived the Clebsch-Gordon coefficients, and because we knew what J3 was like. So we actually derived it here rather than just wrote it down as we first did. We also have a Casimir operator acting on this state. And the Casimir operator is then given by J times J plus 1. So hence this J times J plus 1 that we have standing up here, and this is then 3/4 on the state. I think, let's see, do we have any questions to this? Then we have just a few minutes, but okay, I'll continue anyway with the 3-dimensional irreducible representation. So now we consider J equals to 1. So this is then a 3-dimensional representation. And we want to define our basis for this space in such a way that we have a 1-1 state that is 1 0 0 0, and a 1 0 state that is 0 1 0, and the 1 minus 1 state that is 0 0 1. And the generator J3 should give back the m when acting on this state, m times the old basis vector. So I just want a 1 multiplying this guy, and this is why I have a 1 there. I want a 0 because this one has m0 multiplying this guy, and so I have a 0 there, and I want a -1 multiplying this guy, and so this is why I have a -1 there. So this is then my representation of the J3 generator. Then, knowing the form of J3, I can find, and the action of the raising and the lowering operator. So let's see where we had that. So either from this general form here that we wrote down, or from this form here, we can figure out the shape of J plus and J minus by just evaluating the square root here. And doing this, we find these forms of J plus and J minus. And they're actually exactly the same that we had for SO3, because this is our representation that we have in exactly the same form for SO3 as well. And we can then rotate using this particular representation. So the 1 as in j equals to 1 of j. And for example, rotating around the z-axis, we then exponentiate to generate a j3. So we exponentiate the guy that we have up here, so this guy here, and we get this form. And now if we look at this, we see that here we actually we are actually back to where we started if we rotate by 2 pi. So, however, this is not the case for the SU2 group itself. For the SU2 group itself, we had this factor of 1/2 sitting everywhere. So here it is. Let's go back to the definition. We had this factor of 1/2 sitting there. And that meant that to get back to where we started, we actually had to rotate by 4 pi. So this representation is not faithful, so it's not one-to-one with SU2. It is a representation. It has the representation property with row of G1, row of G2 is row of G1, G2, but it is not a faithful representation. Finally, I should just say that we can also write down the Casimir operator. So now we have found J3. So we know J3 squared, we have found J plus and J minus, and last time we had this form for the Casimir operator. So we can find explicitly that it is 2 times the identity. So 2 times 1 plus 1. Any questions to that? So let's take the break then, and then we will consider product representations of that. So I suggest that those that are keen to have the break, take the break, and maybe someone wants to ask some questions without having everyone around, then that's also fine. So if there are no comments or questions, I'll come back a few minutes before we start again. So I'm back if someone wants to ask questions. Yeah, so Matthias is around. Maybe I could ask you to be a test person.
Yes.
Yes. Good. I'd like to see how well you can see my whiteboard. So I have a whiteboard over here. Something is written on it.
Yes.
Probably I'm not holding the computer completely still.
No.
No, as in this is not going to work.
Well, you're not holding it still, but whenever the text is in view, it's legible. Even now when it's only a tiny little screen thingy, since you're sharing screen.
Right. Yeah. Right.
But the reflections of the lamps are...
The reflections are bad, but that is something one could address with a bit of work. So let's see. Well, can of course get better lamps, but I think that now there should one reflection should have moved slightly at least.
Yes. So that would work, especially if you got some pile of boxes to place the camera down on.
Yeah, I do have that, but I'm intending to do the experiment right now. So for this lecture, it would definitely not fit to have it on the board because it will be a lot of equation next and a lot of lengthy formula, and it's actually quite handy to have them written down already because the sheer writing time takes so long. Or maybe next time it could be an option. So those of you who are still around 1 minute before we actually start, does anyone want to express some opinion on the option of having either tablet or whiteboard lectures instead? So I could consider doing it, but this lecture it doesn't fit quite because there will be lots of lengthy expressions soon. But for the next one, for example, it could fit. But yeah, for me it is working fine, so I'm happy to go on like this.
Could perhaps try it once and just see how it is. Try half a lecture and then ask in the break and if to swap over again.
That could be an option, and this next time could be a good time because it's not as lengthy equations as we will encounter today. Okay, so it's quarter past, so it's time to start again. I'd like to encourage you to ask questions. It's not the intention that it should be a monologue from my side here, but I can only encourage you. But it's not only up to me to make this interactive, it's also up to you. If you're not saying anything, I cannot force you. Okay, so we have considered various representations of SU2, which is of course a group that you know from spin physics. And now we'll get to some aspects that you should have seen in spin physics and quantum mechanics, namely Clebsch-Gordon coefficients and the Clebsch-Gordon coefficient addition. So how you add various spins to get spin this and that. So this is what we will go through now, but we will do it probably more properly than you did in quantum mechanics. We will do it using group theory. And in group theory words, what we will talk about is the direct product space. So what is the direct product? Well, given a M times N matrix A and a P times Q matrix B, the direct product or tensor product or sometimes chronicle product A times B is a matrix of dimension MP times NQ, which is obtained by taking the matrix A and replacing element Aij by Aij times the matrix B. So, in other words, if we have some matrix A, which has some elements A11, A21, A12, and A22, for example, what is happening then is that we make this matrix bigger and insert the matrix B everywhere. So this is then the matrix B, this is then the matrix B, and this is then A times B. And we see that we have this block diagonal structure of this matrix. So this is then the tensor product or direct product of two matrices A and B. And we will use that, and we will use such matrices to act on the direct product space. Okay. So we are interested in the direct in the product of irreducible representations. So we will go through this by considering an explicit example, and I think that once you have seen this example, it will be pretty clear how to generalize it. So we will consider the direct product space of a spin 1/2 and the spin 1 representation. And we start with the basis vectors of this space. Now, actually, the basis vectors are also obtained on this form here. It's just that the matrices A and B are columnar columns only. So the basis vectors that we will use are then obtained by taking the first elements of this larger basis to be the sort of upper state here times a general state here. So it's 1m here and 0 here. Then we have the lowest state here and the more general state here. So it's 0, 1m. So this is now, of course, a three-dimensional guy because we can have the values 1, 0, and -1 here, and the same here. So these objects are 6 entries long, and we can write them down more explicitly. So the very first basis vector in this direct product space, so that is when we have m equals to 1 here, this will be 1, 0, 0, 0, 0, 0. And then for the next basis vector, we will have 0, 1, 0, 0, 0, etc. So this is where we have the 0 here instead of the 1 there. And then we have a third state where we still have 1/2 here, but we have the last state here, so 1 minus 1. And this is then our next basis vector, our E3, so it's 0, 0, 1. And then we have those that have minus 1/2 there, so we have 1/2, minus 1/2, and then we take the highest one here, so 1. This is the next basis vector, so 0, 0, 0, 1, 0, 0. And then I think you see the pattern now, so I have 2 more like this. So this is then the direct product basis on which the direct product representation of matrices are acting. And you should have seen direct products in the discrete part of the group, so I think this should be a bit familiar. Okay, so on this space we then want to act with the representation of some element un of the group un in SU2. So we use then the direct product. So of the first representation, the 1/2, we take the element 1, 1, the element 1, 2, the element 2, 1, and the element 2, 2. And then we insert this D1, so the 1 representation from here. It goes there, and there, and there, and there. This is then the full representation acting on this direct product space with the basis vectors that we had up there. And of course, this is a 6 by 6 matrix because these are 3 by 3. So it's a large matrix. To see the action of this matrix on the basis vectors, it is enough to use material that you should have seen before. I'm not entirely sure if it's still theorem 9, but in a theorem known from the discrete part of the course, or the gray stuff that I'm skipping up here, so you actually don't need it if you recall your discrete group theory. The product state transforms according to the direct product representation. So this you should have proved in the discrete part of the course. So we have then this. And if we now take and write it down for particular representations here, D1/2 and D1, we just insert the respective form of the generator J here. So it's E to I generators, and here we have the 1/2 representation of the generators, and here we have the 1 representation of the generators. This is then some 6 times 6 matrix. But now we want to study the algebra. So we want to study the algebra of this. So what happens to the algebra? Well, the algebra is obtained by differentiating the group. So we want d of ji for some element ji in the algebra. And it should then be this big type of 6 times 6 matrix. But of course, it should be defined as being the derivative of this guy that we have up here in ni direction for element ji. So note that what we have here is a tensor product, but it's a product. It will be in each place in the big matrices. It will be a product of stuff. So we can use the chain rule to take this derivative. So this derivative here is then I, the 1/2, the ni, so this guy, times d1 of u, but evaluated at n equal to 0 because we take the derivative at the x equal to 0, or in this case n equal to 0. So we expand around the identity element to find the algebra. So here we acted with the derivative on this first term. There is also another term where we evaluate this at identity, and we let the derivative act on this space here. Actually, maybe some of you think it's pretty obvious and wants to ignore all of this. This is fine then. What we get is, in any case, that we have the representation on the half space times the identity on the spin 1 space plus the identity of the spin 1 space, sorry, spin 1/2 space with 2 dimensions, times the algebra of ji in the spin 1 space. So actually at the algebra level we get this sum here. So we can also generalize this, and generalization of this is that a tensor product between Lie groups and the representations is defined by t1 times t2 of some state psi1 times psi2, that is d1 of psi2 d times d2 of psi2. Then this statement at the level of the group translates to this statement at the level of the algebra. Now this encircled statement here is what we had before. So we have once the algebra from the one space and nothing happening to the other space, and once the algebra on the other space and nothing happening to the one space. So it is this thing up here. And of course, to prove it, if you don't think it's obvious, it is this sort of exercise to go through. Then an important thing to note is that if we start with bases which are diagonal in which the J-free operator is diagonal in both the 1/2 space and the spin 1 space, then if we act with this direct product representation, since we always get constant times what we had before back, we should have that on the direct product space before. We never jump between states when acting with J-free per definition of J-free. Work with an eigenbasis of J-free. So that property holds also for the direct product space. And when J-free is acting on the first representation, we know that we will get M1 back. And when it's acting on the second representation, we will get M2 back. So in total, we will get M1 plus M2 back times the state. So this state here is the same as this state here. And in other words, this is the eigenvalue of this operator in this direct product representation. And now the eigenvalues of in this case J-free, we call the weights. And we draw a weight diagram, it's called. So what is that? Well, that is a way of trying to arrange all the states that we have in this direct product space. So all the states that we have on an axis where we count M1 plus M2. Well, to get the maximal M1 plus M2, we must have the maximal state here and the maximal state here. So then we have the M1 plus M2, 1/2 plus 1, that is 3/2. To have this eigenvalue being 1/2, we have actually two different options. We can take 1/2 here and 0 here. That will give us a total of 1/2. Or we can take -1 there, sorry, -1/2 there and 1 there. This will also give us a total of 1/2. Similarly, for -1/2, we have two different ways of adding up numbers to -1/2. But again, for -3/2, we have only one way. So we must take the most negative number both there and there. And see, now we will do a lot of calculations here using this direct product space. So we want to consider the decomposition of this product representation. So we want states that are eigenstates of this guy and of J3. And to find all the states, because the states that we get by these direct product representations, they will, although we had eigenvalue basis for J1 and for J3 in the 1 space and in the 1/2 space, the direct product basis will not be the eigenvalue basis that we're looking for. And so we want to find this eigenvalue basis where we have a diagonal J3. So let's see how to obtain that. So that will be sort of the goal for this. And what this means is that we want to decompose the direct product representation into a direct sums representation. So we will have in the end some block diagonal structure. So I think this will become a bit clearer once we get there. Okay, so now we want to consider dj minus, because if we had dj minus, we can easily get dj plus, because this we get by Hermitian conjugating, but it's a real matrix, so we get it just by transposing. So then we would have dj plus and dj minus, and we will figure out dj3. So we can also then figure out the representation of j squared, which will not be diagonal as the basis is constructed. Okay, so first we want to then find dj minus. So we do this by using the relation we had before for the algebra. So we should have the 1/2 representation of j minus times 1 in the other space, 3-dimensional space, 1 space, let's call it. And the unit plus the unit matrix in the spin-half space times that is direct product times the generator j minus in the spin 1 space. Okay, so what is this? Well, have a look. So d1/2 of j minus. So that we found before was 0, 1. Sorry, so not b1. 0, 0, 1, 0. It should be something on the 1 step below the diagonal. So it's this guy. So we take this guy, direct product, the unit matrix in 3 dimensions. So this 0 is mapped to this 0, 3 by 3 0, that 0 is mapped to that 0 is mapped to this 0, and this 0 is mapped to this 1 times 1. That 1 times 1 is later ending up in this block here. So this contribution to this matrix is from this one here. Then we should take the identity matrix in 2 dimensions. Well, this is 1, 0, 0, 1. But for each of those ones, we should insert this big guy here. And this guy here, we have found before that it is this factor here. So it should be something off one step below the diagonal because it's minus, and we found that the normalization constant was a root 2. So we insert it here. This 0 then multiplies the same matrix of this form, but it ends up in this big 0 here. Similarly, we get a contribution, which is a big 0 here. And we get a contribution from this 1 here, which is this matrix again. So the same matrix is standing there and there. So that's how we built up the J minus, so the lowering operator in this direct product space. And J plus we get for free by transposing this. Okay, now J minus and J plus, we can calculate J square. So this is going to be too lengthy, so I'm not going to do it, but I'm just going to highlight that I am using this equation here. So J3, this is this guy we know. So we can square it. So we have J3 plus J3 squared plus the product of J minus this guy times its transpose from this guy here. So that is the ingredients that are used in calculating this matrix. But obviously that is just straightforward matrix manipulation and what a lengthy straightforward matrix manipulation. So I'm not going to do it there. It's not so bad because many elements are 0. However, I feel that the explanation for why J3 has this diagonal form has perhaps fallen short. So let's motivate why we have this form here. So first we note we have 3 elements, 3 half, 1 half, minus 1 half. So every time we are decreasing the value by 1, then we start over at 1 half, and then we're decreasing by 1 to minus 1 half, and then down to minus 3 half. Well, the reason for this is, of course, that this was the E1 vector. So it was this highest vector. It was this vector over here. So this vector here is going to give this eigenvalue here. Our E2 vector had the same 1 half here, but we were down with 1 unit here. So it was this guy here. And this has then the eigenvalue 1 half ending up here. Then our E3 vector will lower this eigenvalue yet 1 more step. So this has got to be E3 standing up here. And this eigenvalue then goes there. And the other eigenvalues for the other eigenvectors having the minus 1 half here, instead of the plus 1 half that we considered, are then relatively lower by 1 unit. So this is how we get the eigenvalues 1 half, minus 1 half, and 3 halves. So this is how we can argue for the form B of J3. Okay, so then we know D of J3, this guy known, and the J minus we calculated, this guy known, and this guy obtained by the transpose of this guy. So we can calculate J square, and we then have this matrix. Some of you might expect J square to be diagonal because there was something called Shor's lemma, saying that if we have an operator that commutes with all elements in the group, it should be proportional to the identity matrix. This is clearly not proportional to the identity matrix. And so I wasn't completing all the details of Shor's lemma. The missing out detail was that if it is one irreducible representation. So this is not an irreducible representation. On the contrary, we will reduce it to two different representations. And this is the reason why we can have this form of J square. So it's not proportional to the identity matrix, and it's not even diagonal. But we want to make J squared diagonal, and we want to reduce this space to a direct sum of different spaces. Okay, so we want to find the eigenbasis in which this is a diagonal nice operator, and also in which J3 is diagonal. It was already diagonal, but we want to keep it diagonal. Okay, so let's have a look at this matrix here. Well, if we stare at it, we pretty soon discover that we do actually have two eigenvectors. So this guy and this guy, will be the only contributions acting on E1, which was something like 1, 0, 0, 0, 0, 0. And E6, which was something like 0, 0, 0, 0, 0, 1. So E1 and E6, they are actually already eigenvectors. And we find here that the eigenvalue is 15/4. So there are at least two eigenvectors with eigenvalue 15/4. Now, this constant 15/4 is not at all uninteresting, because we call it eigenvalue of J squared should be J times J plus 1. And if we take 3/2 times 3/2 plus 1, this so happens that this gives us our 15/4. So then we know that one of the representations in this direct sum representation, as it will be, should be the 3/2 representations. Now that should be familiar, because when you added spin, you should have seen that you can have the maximal spin that you get is the one that you get by adding the spins. So 1 plus 1/2, that is 3/2. And so we have found such a representation. Good. But we have only found one eigenvector. We want the others, and one could of course attempt to identify more eigenvectors of J squared. But a more direct way of obtaining all the direct eigenvectors would be to act with J minus. So we know the form of J minus because we have calculated the form of J minus with this direct product sum. So let's act with J minus on this state here, 3/2 plus 3/2. And there's a little 4 here indicating that it must be a 4-dimensional space, because we should have the eigenvalues 3/2, 1/2, minus 1/2, and minus 3/2, because we have seen that m changes in units of 1. Okay, so this we know that we will have. So we have the guy corresponding to this eigenvalue, and then we act with J minus, and we should get something proportional to the guy with this eigenvalue. Okay, so now let's act with J minus here. So J minus on this state. Then I have this factor here from the equation we had before with the J minus. So it was a big root, and then the state with 1 lower. And in that root, it was J times J plus 1 minus M times M minus 1 for J minus. So we have this factor here, and it turns out to be root 3. So it's root 3 times this state. So this is the state that we want in this 3/2 representation. Now let's see at the state that we get when we act with J minus. So we act then with J minus in this direct product form. So recall that once we should act on this representation, do nothing to the other, and once we should act on this representation and do nothing to the other. So here we act on the first representation and we do nothing to the other. Then we do nothing to the other and act on the second representation. So this guy here acting on this 1/2 representation, well, I know I must have a -1/2 there, and then there is a proportionality constant that you may remember was 1, or you don't remember, it doesn't really matter. So the point is that we have this state, and then nothing happened to this state, so it stays here. Then we have the other state where we did nothing to this guy standing here, and we acted on this guy, and we should have something proportional to the 1, 0, and the proportionality constant we have seen was √2. So we should have this state, and we get this state. So we should get something that is √3 times this state, and we get this stuff. So dividing out this √3, we see that this thing must be this thing. Or in other words, the 3/2, 1/2 state, the 4-dimensional representation, is this thing divided by √3. So it's 1 over √3. This thing goes here, and 1 over √3 times this thing. So it's 2 over 3 root of that, and then this thing goes there. So we have found, after some algebra, this state here, from possibly somewhat tedious, but in principle uncomplicated algebra, we have been able to identify this state. So in this way, we have found, we had the 3/2 3/2 state, we have found the 3/2 1/2 state. Then we can repeat this exercise to find the 3/2 -1/2 state. So by similar steps as up here, we find here the state 3/2 -1/2. So that involves acting both on the product representation and on the 3/2 representation to get to the normalization. And in this way, we can conclude that we have this result here. So I'm not going through the steps again because they are very similar to before. You can check them in the notes here. So in this way, we have then found 3 of the states. Luckily, we don't have to do it once more because we know that we should have something with eigenvalue -2/3. But going up here, we see that we actually already know what the state was. This must be the E6 basis vector itself. So, and we have already found that that was also one of the eigen states of this operator with this eigenvalue, so the same eigenvalue as up here. So this must be the state that we are searching, so we don't have to act with J minus once again to find the lowest M state here. So we can collect the pieces that we have assembled, so the state that we started with, and then we lowered it with J minus twice, and we got 2 more states, and then this guy we could actually just write down. So here we have collected the pieces from upstairs. That's 4 states, and they correspond to this J3/2 representation, and we should exactly have 4 states, so we have found all of them, but our space was 6-dimensional. So there is something more hiding in this space. the hiding representation can be at most two-dimensional, because there's only 2 dimensions remaining. And it is exactly 2-dimensional, otherwise it would have, would have a trivial representation, it wouldn't be interesting. So we have this J1/2 representation here with dimension 2. So spin 1/2, there are 2 states. Okay, so then we want the vectors then, the eigenvectors of J3 that are within this representation. So we know that the spin should add up to 1/2, and there are 2 states that have this property. So one is 1/2 0, and the other one is -1/2 1. In both case, we add up the spin to 1/2. So which one of these should we take? Well, we have actually already used up one linear combination of these 2 states. We have used up this linear combination here. So this is taken. So we must take the other linear combination of these 2 states. That's orthogonal to this. So now we are calculating the scalar product between this state here and some linear combination of this vector and this vector. So A times this vector and B times this vector. And we want that scalar product to be 0. So multiplying out this, we then find that this is satisfied if this equation here is satisfied. So the orthogonality requires this. So we take A, for example, we can take A to be √1/3 and B to be minus √2/3 if we also normalize. So the √3 is such that A squared plus B squared squares to 1. And seeing, well, it's you can easily check that in this way you will also have the orthogonality with this state up here. Okay, so then we have found one of the states, the 1/2 state, as the orthogonal combination. So it was then this state. And actually, J square here on this state should now be just 3/4, because it should be 1/2 times 1/2 plus 1. And that one can check as well. So now we have actually found 5 basis vectors in this state, and we can obtain the 6th one by acting with J minus on this state here. So we know that the 6th state must be within this additional 1/2 representation. So acting with J minus on this state here, we should get it. And again, it's some algebra to obtain that it is this linear combination here. Alternatively, we could have found the same state by requiring it to be orthogonal to this guy. But actually, then we would have in principle a phase remaining. So it's nicer to do it the way we're doing it. Okay. So to wrap that up, we have now found two new basis vectors that are in the 1/2 something representation. So J is 1/2, and they have some form. So now by construction and by the invariance of J square under irreducible representations, we find that J square can be divided in two different pieces. So one piece corresponding to the free 1/2, to the free half representation sitting up here. There, the eigenvalue should be 15/4. And one piece corresponding to the 1/2 representation sitting here. So it should have eigenvalue 3/4. So we see that we have this block diagonal form of J squared of 3/2 and J squared of 1/2. Also, this is also we can then, well, identifying the rotation matrix between the direct product basis that we obtained immediately and this new prime basis, we can find the form of any vector here. And we will find that we always have this, so we always have this block diagonal form. So we have, what we have done is that we have rewritten the direct product representation as a direct sum representation. So 1/2, you may sometimes express it as 1/2 times 1 is 3/2 plus 1/2, or if you prefer to count the dimensions, 2 times 3, so the dimension of this, the dimension of this is 4 plus 2. And here we should note that 2 times 3 is really 4 plus 2. And that's a very good double check, because that means that we haven't lost any degree of freedom. So we have recovered the full space here. There's nothing lost. So we have decomposed the direct product representation into a direct sum representation, where now everything is block diagonal. And this can be done in general. So the tensor product of irreducible representations can be expanded as a direct sum of irreducible representation. So dj1 times dj2 is then a sum with some coefficients of irreducible representations. And this here is called the Clebsch-Gordon series. So I was hoping to get to the Clebsch-Gordon coefficients, but I see now that that is too much. We will not get to the coefficients, but we will not find how to relate the states in these different bases, that we will have to do next time. But we have found that we have this direct product representation. I think that if I don't get to the direct product representation, I can stop here. There is a graphical representation of how one can add up the spins and identify the different representations that one will have, but that we will do next time then. So let's first see if there are any questions. I think there should be some questions, because I don't think this was super clear. But if not, to wrap up, the point is that we have once again taken the direct product representation and made it into a direct sum representation. The direct product representation itself was ugly and messy. The A square was not even diagonal, etc. But it can be turned into a direct sum representation where we have matrices on a block that it corresponds to the 3 1/2 representation, and on a block that corresponds to the 1/2 representation. But if there are no questions, let's call it a day. And again, I will hang around for those that have questions for a smaller audience, and I will see, I hope, most of you tomorrow for the exercises. So thanks for today. So any questions? So if there are no questions, I will end.
I found one thing that I'm thinking about. In
Yeah.
equation 469, we pick A and B. What determines the sign of A and B? Why can't we pick A as negative, or is that just a convention?
So here we can pick A as negative instead. And what will happen then is that we get minus the state, because then we are swapping as well. So we get minus the state, and that will follow through when we act with the lowering operator. So everything will work through, but we will work with minus the states, and all the states within that representation will then go to minus themselves. But they will still have the same eigenvalues. They will just be.
Yeah, well, they will just be a minus. I'm just thinking if it's a convention.
Now, yeah, in principle, that is a convention. However, if we had tried to obtain this state here by saying that it should be the state that is orthogonal to this state, then we would have had to watch out, because this state should also be obtained by acting with the lowering operator on that state. So there we could have made an inconsistency in the choices. But
yeah, if we would have picked
the
wrong negative
exactly.
for that one, if we just did it faster.
So if we could have picked both by saying they should be orthogonal, we could have picked them in an inconsistent way.
Okay.
But we, in principle, for the first one, or whatever one you choose to pick, you could have picked the lowest state as well and act with the raising operator instead. It would also work. But for the first one, you had a degree of freedom.
Okay. Thanks a lot.
Yeah. Good. So, no more questions, or? Okay, then I'll end this meeting. Thanks for today.